Thank you for enabling me to to speak here. It's not for the first time, and I hope it's not for the last time as well. So this is a sort of expository character of presentation, which will be concerned with integer sequences. And it has been done in collaboration with Gérard Duchamp, Maxime Kontsevich, and Gleb Koshevoy. And I will talk in short time about the tools which are used for this talk. So first tool, which is very important here, is the famous Encyclopedia of Integer Sequences. Online Encyclopedia of Integer Sequences, which has an address https://oes.org. And in order to be precise, I took contact with a fellow who established this electronic organization with database, Neil Sloan, on 12th of November, and he gave me the following informations. On 12th November, there were 390,000 sequences in this database. There are 1,000 sequences coming per month as new sequences. And there is 14,500 registered contributors. And another quite incredible information is the number of hits per day, which is 1 million. And of course, I was unable to check this data, but knowing Mr. Sloan, who didn't lie for the last 60 years of existence, I believe roughly what he says. Okay, so this is a very important tool for us. And the second tool is computer algebra systems. Systems very much used by the audience here. We have here real masters. I will not mention their names because everybody knows them. So in order to talk about the parametrized algebraic equations, I have to first mention a case of non-parametrized equations in order to see what we parametrize. And first example will be a well-known sequence which has been used in many presentations. This is so-called Creveras sequence. Creveras sequence, I see already Aline who is smiling. So I give the Creveras. I give the formula for n 3n divided by n plus 1 and 2n plus 1, which is 1 to 16. Okay, so this is a sequence of integers, as you see, and the questions that we ask are the following. What is the generating function of this sequence, and what are properties of the generating function of this sequence? And another question which we will not treat here is, are these numbers here moments of something? It turns out that yes, but this question will not be explicitly treated here. So I will write down the generating function of this sequence, which I will call h of z, which if I call them a of n, can be expressed through hypergeometric function 3, 2, and you have here 1/3, 2/3, 1, 3/2, 2, 27z. Okay, so you see here this hypergeometric function. In question is
original definition of Creveras? No.
I believe so.
Yeah.
Yeah.
No combinatorial?
No, I'm not talking about combinatorial derivation of this, but I'm talking just about this series of integers. And maybe you're deceived, but I can't do much. So you see here, there are two things which we notice, that some of these coefficients are larger than 1, and the criteria for algebraicity tell us that we should take the fractional parts of these things here and see what happens then. If we take fractional part of coefficients here, we get f(3, 2), and we get 1/3, 2/3, 0, and 1/2, 0, 27z. So immediately we see that the zeros are cancelling, because these are upper parameters, lower parameters, and we are left with a very nice situation in which the coefficients in upper coefficients in upper series and lower series interlace, and this is the condition for algebraicity of this function. And okay, we have a condition, but we still don't have this function. And now it turns out that this function can be obtained very easily using computer algebra systems, and it has a following form. We define this 1 minus 27z as S, and this h of z is 27 for z s minus 3 I square root 3 sorry, I have a tendinitis. 2/3 S of 3 x, z plus 1/54 plus I square root 3 z 2/3 minus square z 27 plus complex conjugate minus S81. Sorry for bad writing. What is important here is that we have here a complex numbers, and the function is a real function, and you see from that this is a radical. So this function is algebraic and is explicitly obtained. Okay, and now so this is a case, one of many cases that we can treat in a similar way, but still there are no parameters. So now I will talk about certain ideas which appeared already many years ago, but they have been made concrete by the work of several people. And these ideas concern certain transformation of integer sequences. In fact, they are also true for some non-integer sequences, but okay. So this is a transformation which has been mentioned 20 minutes ago by Thomas, but in slightly different context. So x sum n equals 1 infinity c of n t n equals n equals 0 a of n t of n. Okay, so I have chosen the name C and A for funny reasons, because many of us have seen a similar formula in the combinatorial context, because this is with slight modification the content of so-called exponential formula of combinatorics, whereas here we have, apart this n, we have ordinary generating functions here also. In combinatorics we have exponential generating functions. And I will call this transformation x of c of n equals a of n. And why this transformation was interesting for us? Because it appears in the context of algebraicity in the following way. Namely, they are powerful theorems which say that if a of n generates a generating function which is algebraic, then c of n generating function which is also algebraic. I don't say function, I say Cn algebraic. This is a simplified version of the theorem which has been established by Kontsevich.
It's a trivial result, yes.
This is logarithmic derivative.
Yeah, but many things are...
No, it's not.
Okay, but it has been also treated by Reutenauer and by several people, including Alin Bostan, and by Sergei Kirov. And it is present in the Encyclopedia of Integer Sequences in many places as a means of deriving ordinary generating function of an. And I have looked at this formula from a very primitive point of view. Namely, I wanted to choose some very well-known formulas for Cn, and I wanted to see what it results in if we substitute for An simple formulas. And I give you some examples. Now, I am using the notation from encyclopedia of interrelated sequences. Six-digit number. This is a number in the encyclopedia. So I have defined this transformation x, and I'll give you some examples what it gives. So x of binomial 3n of n gives 3n of n binomial divided by 1 of 2n plus 1. Okay? Now, the same for 4n, the binomial, 4n over n. This gives 4n n divided by 3n plus 1. In general, x of Pn gives Pn n binomial divided by p minus n minus 1 n plus 1. Okay? And these numbers for p integer are called Fus or Fus-Catalan numbers. So this transformation brings pure binomial to this kind of Fus-Catalan numbers. Okay? And for p equals 3, these numbers are A, O, O, this 117, 64, P equals 4. This gives a 22. Okay.
The most important are Catalan, of course.
Yes, for 2. Yes, for 2. For 2. Okay. Yes.
You also here you have so many equivalent definitions like Stanley for Catalan. Catalan is 500.
Yes, we know.
But how is here?
2. P equals 2.
Yeah, but for P equal 3.
These are different functions, different numbers.
How many equivalent definitions?
For P equals 3? Not definition, interpretations. I'm not talking about the interpretation. Okay, so this is this is not the subject of my talk. So this is an example of relation. Now, a second example, which I will give, is that if we take another binomial, Pn1, this gives something different because it gives Pn plus P minus 2 binomial divided by 1 over n plus 1. So these are different numbers because here's minus 1. So then we see that here we are in the domain of algebraic equation, because these binomials have algebraic generating functions, and the results of transformation Ex also have algebraic generating functions. So we are now in the domain which is well understood, because we know that both objects here are generating, have algebraic generating functions.
Karol, the last formula is for which p? Equal 2 also, 3 or something? Last formula.
Yes, for 2.
For p is 2 is also?
Yeah.
So is Catalan then?
Yeah.
So the most important. Good.
Okay. So now we want to extend this thing into formulas which involve slightly different slightly different sequences. And I can give you only a small choice, because there are two situations which I will enumerate. First situation is that, which is similar to that one, that if we make a transformation X, then we can identify what it gives. Okay? In these cases, we could easily identify. Now I will quote two cases where the identification of the result of transformation X is more involved. So now AN equals P to N, and now you have two parameters. You have P plus R N over P N. So this is a binomial symbol which is characterized by two parameters. So I should write A, P, R, N. Okay? Now, for P, which is integer, this sequence is a sequence of integers. But it turns out that it's also a sequence of integers when P is rational. So when P is rational, it is also a sequence of integers. So now I will give you the result of transformation of type X, and I will give you what is the result. The result is slightly more complicated because it's P plus R times P R N plus 1 plus P. And here we have a binomial system which is shifted par rapport with respect to the initial plus R P N. Okay? And it turns out that this sequence, which is a result of transformation X on that, is also an integer sequence, which, however, for most of the values of P and R is not in the encyclopedia. So we are somehow going outside the known sequences, but we can show by explicit use of computer algebra systems that the generating function of this sequence is algebraic, and generating functions of this system is also algebraic. So we somehow have a production of algebraic equations, which are, however, now parametric. Okay, and I'll give you now another two examples.
So R is 0, 1, 2.
Yes, it's all. Yes, R is 0. No, let's say 1, 1, 2, and P is also, let's say, 2, 3, and so on. Okay, but as I said, P, it works also for P, which is rational, and I will give you an example in a second. Now, but now there is a tendency to think to use another set of sequences which are let's say a little bit less parametrized, but whose generating functions are known to be algebraic. And I will give you one example which is extracted from the long list of sequences which are known to have algebraic generating functions. To n well, so many of you will recognize this sequence which appeared in many presentations from 2018 when it was suggested to us by Maxime. And now here situation is much less clear because we don't know exact form of functional form of result of this transformation, but we don't need exact form. What we need is the sequence of values, and with this sequence of values, it's enough to get an algebraic generated equation which characterizes this, and this is of the 6th order, but we have an exact formula for algebraic equation, but we don't have a functional form of these coefficients, because there is a wonderful property of computer algebra systems that it's enough to have a very long series of values, and then the generating function is somehow reproduced. Okay, so this is a different case, and now the last case, which are in this series I will present, is another series of integers which are let's say this concerns integers number 2, 1, 1, 4, 1, 9. Okay? So this I will write them here. 6n factorials, 2n factorials, 4n factorial, 3n factorial, and n factorial. So, sorry. So this is the sequence under this number in the encyclopedia, and the result is known. So I can write down, it's a long formula involving a couple of gamma functions. I will not write it down, but we know it. So in the contradistinction with this sequence gives a known expression for the transformation x. Pardon? Yes, of course, because this is a part of the series of Bober and in the paper of Bober. But here we don't know what is the result, and here we know the form. I have it in my computer. So now I stop with this thing that you see that in certain cases we can really have a parametrized equation with some parameters, not in all cases, and we can give a precise form of parametrized algebraic equation. And now I am going to show my slides.
But for other types than Boyker and Heckman?
Pardon?
For other types from Boyker and Heckman, so...
Yes, I can do the same experiments. So I cannot guarantee that I will know what is here on the right-hand side.
No, but hypergeometric is also the Lambert.
I'm coming to this problem now, okay?
So how do you prove the first example is algebraic? By
Which ones?
the one where you write question mark. No.
This one? Because this is... because I calculate the algebraic equation. Without, you see, if I take this transformation x, I get a infinite number of integers. And with these integers, if I feed them into special procedure, this procedure will give me algebraic equation. Okay?
No, but it was actually an abstract result by Reutenauer, like...
Yes. Yeah. Okay. But
I think you need something that you calculate an algebraic equation which holds up to some.
If I take 673 case members, this procedure gives me the precise equation, which I can check. So I don't need explicit value. So now I am coming to the thing which is related with one of these. Yes, it is related with this case. Okay, so these are so-called Fuss numbers, and I will explain you. You see, this expression, which I have here surrounded in red, is exactly the second form of so-called Fuss numbers. And the first form enters this generating function, which has been proposed by Johann Heinrich Lambert in 1750. And it is defined here. It's convergent for some environment of 0, and it has these three expressions, which I've written because it's not evident that they are all equal when you are working with them. And these sequences parameterized by P are here from the encyclopedia. And 20 years after formulation of this function, Lambert noticed some strange behavior, namely the rth power of this function has the property that the exponent r appears in 3 places. And the character of the expansion is very similar with a small small renormalization of 1, which becomes r, and everything is multiplied by r. And these functions, these numbers here, are called Fuss-Catalan numbers, and they are very important in the free probability. So we have some works with Młotkowski and so on, all this thing. So you see, this formula, which looks very strange, is valid for any P and R real. Okay, so it's an amazing formula. I want the next slide, but it doesn't.
Yeah.
Oh yeah, okay. And now, why this thing is important for us? Because you ask the question, how do I know that, for instance, binomial 3n over n is algebraic? So our ambition here was to derive explicit parametrized form of algebraic equations. And it turns out that these functions BP from the previous slide, they satisfy an extremely simple functional equation, which is here, which is of order P. Okay, this is a well-known equation. Yes, exactly. I am basing myself on information from the book of Knut. And there is another extremely important relation which involves this BP, which is written here. Okay, and it is still parameterized by P and by R. And what is important, that R enters here pure binomials, not divided by anything. So that's why we will be able to answer your question, because we can manipulate these two equations, A and B, in two cases, R equals 0 and R equals -1. And the function which interests us is, first of all, the function dp, which is a sum of pure binomials, and the function for r-1, which I call ep, which is now the function involving binomial with -1. So this is one of the cases which I presented before. And you ask whether, how do I know that it is algebraic? In fact, by combining these two equations, I can write down explicit functional algebraic equations for these two functions, d and e. And they are both of order P, and they are explicit. So they are parametrized by P and explicit. So we, at least for these very simple cases of binomial and binomial shifted by 1, we have an explicit formula. And then now I will just show you. I don't know why. Okay. So now you see this equation which I printed out for several values of P. They are looking very nicely and logically, but if you get them for the first time from computer, you don't know what is the exact form. You have to combine and think. And I have the exact form, and now I have the same thing for the shifted by 1. Okay, so these are exact equations. But that's not the end of the story, because now I told you that this Lambert function is also valid for fractional values of parameters. And I have chosen the simplest example, which is fractional value 3/2. So, oh, sorry. Here you see this Lambert numbers for 3/2, but are not integers. What you need to transform them into integers, you multiply by 4 to the power n, and then you get integers. So now I am calculating the generating function of this fractional number, the Lambert numbers, and I get something which is logical. I don't get one hypergeometric function, I get 2. Okay? But we can show that both of them satisfy interlacing condition of Boyker's and company. The first one is evident, and the second one is when you take fractional parts. If you take fractional parts, you get this thing which is clearly interlacing for the second one. So we know that even for fractional parameters, it is algebraic. But we need to know what is the form of this function. So now I have localized this sequence with 4 to the n in the encyclopedia, and I am calculating the generating function with this parameter 3/2. And then I have b of 3/2, but not of z, but of 4z, because I had to include the factor 4. Okay? And I give that to the computer, and I get something which reminds radical, but it cannot be seen as radical with the bare eye, because this function doesn't look radical. But with some tricks which I have no time to explain you, it can be brought to the radical form, and you can develop this funny function and calculate the equation which is of this form, which exactly reproduces parameter 3/2 from this function. So this is also equation, cubic equation. And now I come back to these Fuss numbers, which appeared already in several places. And I look at them, and I calculate generating functions of all these numbers, Fuss numbers, as a function of p. As a function of p, p is here, and I here see a nice sequence of hypergeometric functions which have one defect, namely one of these parameters at the end of lower series are larger than 1, so we take fractional part. Okay, we take fractional part, and then we can write down the general formula for these Fuss numbers, and it is here equivalent to the BP that I've seen before. And as a last thing, I will make contact with a very historical element which dates from the 19th century. It is the problem of Eisenstein, which is very much related to the value of p equals 5. Why? If I take p equals 5, I have this solution b5 of z, which is written here. I don't take a fractional part because for calculations I don't need to do so. It's only for theory I need. Okay? So I calculate now. I write down. I have no calculations to do. I write down the functional equation of b5. So this is a thing that we have seen on previous transparencies. And the next step is to slightly deform this function b5. And I do it in a specific way. Namely, the variable z I replace by variable minus t to the 4. And you see 4 is just 5 minus 1. And then I multiply the whole thing by this new variable t. And I get this function f43 with the modified variable and multiply that t. And then I take my computer and I calculate the algebraic function satisfied by this function which has been deformed by this change of variable. And I get something which is exactly what Eisenstein wrote how long time ago? Very long time ago, okay, which is a quick... What?
100 years ago, something.
Something like that. And which is the functional equation which he solved, which is a quintic equation. He solved that. And now the main point is that this transformation, which I've done for p equals 5, can be done for any p, including p fractional. I will just give you a thing for p which is integer. So I can write down, for instance, not quintic equation, but I can write equation for p equals 17, and I can write a solution of this equation. And now Eisenstein, of course, didn't have a proficiency with the hypergeometric functions, but if you develop this function b5, which is now deformed, if you developed as a function of t, then you get exactly the terms which appeared in the Eisenstein solution. So here we have a general solution for p, any p which is integer. Okay? So now the last remark, I'm finished or I have still 30 seconds. So the last remark is that in this last part, the dominant role was played by the Fus-Catalan numbers, which appeared here, as you see. Oh, sorry. Now, there is a series of recent works by two fellows who are called Wilberger and Rubin, or Rubin, I don't know, who proposed to generalize Fus-Catalan numbers with the purpose to solve another type of functional equations, not of this form, but of much more complicated forms. And they claim that the use of these generalized Fus-Catalan numbers will provide a solution of unknown type, which, because it's very easy to write down the equation, but it's very difficult to write solutions. So you see this combinatoric thing and algebraic criteria have a very down-to-earth applications for algebraic equations. Okay? So that's the end.
Questions, remarks, or elements of discussion for 5 minutes, say?
I can maybe say only
Yes.
that I like very much that Professor Penson teach us the hypergeometrical and nice mathematics and physics. I hope this is physics somewhere, because I remember some years ago you teach me in Poland that is connected with harmonic oscillator somewhere, some business. So I hope that here also will be some other application, and also because I'm working with free probability, and that Fus-Catalan numbers appears as an infinite divisible law So this is like Levy. So that should be excellent.
Yes, I agree with you.
I wait for the next direction.
Other questions, remarks? A little comment short, due to the influence, we could after launch physical combinatorics. It has a sequence that Vincent Rignasso can comment on. So maybe it's time to close the day and thank the speaker again.